Hello, this is video section 7.8 and it's using exponential and logarithm functions. So let's get to it. So we've got three things of vocabulary: rate of continuous growth, rate of continuous decay, logistic growth model. And then what we're going to do is we're going to learn to use logarithms to solve problems involving exponential growth and decay and using logarithms to solve problems involving logistic growth. All right, so let's get right into our first key concept. So we know exponential growth and decay. So exponential growth can be modeled by the function f of x equal a times e to the kt, where a is the initial value, t is time in years, and k is a constant representing the rate of growth. Exponential decay can be modeled by the function the same thing, except for k is negative. So again, k is the rate of continuous decay. Here, the rate k is the rate of continuous growth. And how do you know it's a growth or decay? K is positive for growth, and k is negative for decay. So what is rate of continuous growth? So let's look at that. So basically, it's just the rate of continuous growth is just k, a constant k, which represents that rate. It's positive, it's continuous growth. So the rate of continuous decay is just the value of k in a continuous growth function here, where k is negative. All right. So let's look at a real world problem. When will we use this? So basically, it's just a formula. It's kind of what we've been doing, principal times an exponential function. Slightly different, but basically the same. So here we're talking about chemistry, so don't get confused with all these fancy words. The half-life of a radioactive substance is the time it takes for half of the atoms of the substance to disintegrate. Exactly what it says, half. So half-life of carbon-14, carbon is the substance, the atoms, is 5,730 years. So it says it takes 5,730 years for carbon-14 to disintegrate in half. So whatever the value is, the beginning, for it to disintegrate to half, it takes that many years. Determine the value of K in the equation for the decay for carbon-14. So basically, we start off on this problem. We start off with our function, our equation. Is what we have to start off with. So it's going to be y equals a times e to the negative k t, because we have a decay, we're saying it's disintegrating. So what we know is the initial amount of carbon we say is a, and we don't know the rate, but we know that it takes 5,730 years to get half of this. So we can say 0.5a is equal to a times e to the negative k times 5,730 years. Because they're telling us it takes this many years to get half of the initial amount. So now we just use algebra and logarithms to solve, and we're going to divide both sides by a. And we're going to get 0.5 equals e to negative k times 5,730. Now we just solve. Can't we take the natural log of both sides? When we do that, we're left with the natural log of 0.5. I'm going to put this so I know what my argument is. Remember, natural log represents the base of e. So when you have the base of the argument, the same as the base of the log or natural log, then it's simply the exponent. And our exponent, so this cancels out to negative k times 5,730. Now we need to solve for k, so we divide by negative 5,730 because we want k to be positive. And we can simply put that in our calculator and we get k equals 0.00012, right? And our equation is y equal a to the e, and it's negative. to the negative 0.00012 t. So there's our equation for carbon-14. All right, let's look at the next equation, the next problem, example. If my computer works with me. All right, so now that we have the value for K, we have our formula, now we can use that formula to date fossils. So look at example 2. A paleontologist examining the bones of a prehistoric animal estimates that they contain 2% as much carbon-14 as they would have when the animal was alive. So we're saying these bones now have 2% as much as when it was alive. How long ago the animal lived? So again, we've got our formula that we found on our previous problem, which is right here, which is y equal a e to the negative 0.00012 t. Now, what information they give us? Well, we need to find t, but what we do know that at that t years, we're saying how long ago did it die? And when they say how long ago did it live? So how long ago did it die? So we're saying at that point it has 2% carbon. So I can say A, so I can say 0.02, because that's what 2% is, of A equals A times e to the negative 0.00012 t. Divide by A and I get 0.02 equals e to the negative 0.00012 t. And then I take you see here, they take the natural log of both sides, because I can do that. These cancel out, so then you have the natural log of 0.02 equal negative 0.0012 t, and you solve for t, and you get t is approximately 32,600 years ago is when that animal lived, whatever that dinosaur animal they want to use. And if we put that back in our calculator, we'll get 2%. Okay? All right, so if prior research points to the animal being around 20,000 years old, how much carbon should be in the animal? Okay, so now we're looking for Y, the amount of carbon. So we put 20,000 for T, but what is A? Whenever you're solving these kind of equations and you're solving for Y, you're solving for the percentage or the fraction of the decay, we always use 1 as an original amount. So A is 1. So they fill in A with 1 and T with 20,000, and when you calculate and put this in your calculator, you're going to get 9%. So there is about 9% of carbon in the animal. All right, so it's just kind of being familiar with this and understanding that half-life means half of the amount of carbon. It's not a fancy word. It really means half of its life. All right, so let's look at this continuous exponential growth. So we said, oops, I think we missed the formula here. And we did. All right, so we've got two formulas that we need to know. One for continuous compounding, and then one for population growth. Okay, so you see that they're similar to the exponential growth equation. A equals P times e to the RT, and Y equals A times e to the KT. So you have an initial population at time t, and rate of continuous growth. Again, you have the initial amount at time t, and the interest rate. So let's use these formulas to real world problem. So I tell you, in 2007, the population of the state of Georgia was 9.36 million people. In 2000, it was 8.18 million. Determine the value of K, Georgia's relative rate of growth. So we start with our formula, y equals a times e raised to the kt. So in 2000, there was this many people. In 2007, there was this many. So we're saying that the initial time was 8.18 in 2000. Okay, we know in 2007, which would be 7 times 7 years later, we have 9.36. So we put that in our formula, and we simply can solve for k. But first, we have to divide both sides by 8.18. So we're left with this. Then we take the natural log of both sides, and this e goes away. It becomes equals 7k. And we're left with natural log of this. When we take that value and divide by 7, we get k is approximately 0.01925. So Georgia's relative rate of growth is about this, or about 2%. Because you multiply by 100, you get 1.9, which is about 2%. Now look at B. When will Georgia's population reach 12 million people? So we start with our formula. We know our initial amount is 8.18. 12 million people is what you're going to equal to. You need to find t, the time. Okay, because we know our rate of growth is about 0.01925. We're not going to use 2%. We use the one that's not rounded as much. Then it's just solving. Okay, again, this 8.18 times this, so we divide both sides by 8.18 using algebra. Then we take the natural log of both sides, so we get rid of this e, and this side simply equals 0.1925, the natural log of this. Then we divide by this rate, and we get t is approximately 9.907 years, which means the population will reach 12 million people by 2020. Now, here they say Michigan's population in 2000 was 9.9 million and can be modeled by this equation. Determine when Georgia's population will surpass Michigan. So you want to say, when is Georgia greater than Michigan? So we substitute for Georgia's population its formula, and then we've got they give us Michigan's, and then now we just solve for what? Time. They want to know when, so we're looking for t. So again, we take the natural log of both sides. Now, what do we have? Look at our argument here. It's really important to understand. This is why I said you've got to know what the argument is. The argument is 8.18 times e to this power. This argument is 9.9 times e to that power. Can't we use the product rule and expand them? That's what they did here. So you take the sum of both because they both have a base of e. Now, what do we see? What do we know about this term and this term? Because it's a natural log of e, that goes away and it's simply just equal to its powers. Now we can use algebra to move this t, the right side, to the left, move this natural log 8.18 to the right, and this is where we have this step right here. Then we divide both sides by this coefficient. So then we get t is greater than 11.6. So Georgia's population will surpass Michigan during 2012, over 11 years. Okay, so now one more thing to consider. So we've got these equations that give us growth. All right, now a population represented in Georgia's growth is what they give us in example 3. So according to that, the population will be about 1 billion by the year 2130. Is this really logical? Now, according to an exponential growth, it increases without bound, meaning it goes on forever and ever. So we could get up to like trillions, quadrillions, I don't know how big they come. But that's not logistical, right? We have different things that impact or give us limits, like maybe food supply. Was there a war? Was there a disease? What about the living space? How much room is there in that city to grow? Available resources and just unlimited things that people die. So logistically, even though we have this growth function, we know it's going to cap somewhere. So an exponential growth is unrestricted, meaning it will increase to that bound. But a logistic growth model, which is our last vocabulary, just represents growth and has a limiting factor. Okay, so let's look at this formula. So we actually have a formula which you'll need to know. It says if A, B, and C be positive constants where B is less than 1, the logistic growth is represented f of t equals c over 1 plus a e raised to the negative bt, where t represents time. So let's look at an example, what we're talking about. So it says the population of Phoenix, Arizona in millions can be modeled by this logistic function, f of t, where t is the number of years after 1980. Okay, so this model is based from 0 being 1980. So they want you to graph this function, but they want you to restrict the domain. So they're telling you t, because t is the x, right? So that's the domain. They want you to restrict it between 0 and 500 inclusive. Okay, so 0 to 500. So you would graph it, and you would start from 0 and then go to 500. What is a horizontal asymptote? You see it's a increase. So it's going to have a horizontal asymptote here. You haven't learned this, and you'll learn it next chapter. But for now, you can say the horizontal, you can tell it's approaching 2.1, but that's not our asymptote. Our asymptote is y equals 2.0666 is the asymptote. It's approaching, but it will never hit. So will the population increase indefinitely? If not, what will be their maximum population? No, it's because of this horizontal asymptote in this equation, this function, said no, it's probably going to top out about 2.06666 million people. A little less than that is what will reach its maximum. According to the function, when will the population of Phoenix reach 1.8 million? If you look at the graph, it's about 50 years. Well, how do we do that? We can use our calculator and find that value. Or we can say, let this equation equal 1.8 and solve for t. If you do that, you'll get 50.35. So the population of Phoenix will reach 1.8 million by 2031. Because remember, it started at 1980, so you have to add 50 years to that. Okay? Do the practice problems, and we will see you in class.